Show. I'm your host, Jordan Bingham. Did you know the Smithsonian Museum has a space history department? The collections curated there tell a story and also give us a peek into our future. Today we have Dr. Matt Shindell, curator at the Smithsonian National Air and Space Museum, and Dr. Meg Abraham from Aerospace, who is co-located at NASA Ames Research Center. Over to you, Meg.
Hello, Matt. It's wonderful to finally get to meet you face to face, even if it is electronic. And I'm excited to discuss with you, your adventures in science and the history of science, which is something that I feel extremely passionate about. I almost went into that field, and then aerospace sucked me in, and I really enjoy that too. So I get to live through you vicariously now. And with that, I was kind of wondering if you could let me know what led you into the history of science and space history and museum studies.
Yeah, well, I love that question because, when I tell people that I work at the National Air and Space Museum, I often get the reaction, wow, that's like my dream job. How did you ever end up working at the National Air and Space Museum? And when I answer the question, it really lets me give that person the notion that, it was a very long and winding road that I never really imagined would end up at the National Air and Space Museum. I started out thinking that I was going to go into science and engineering. When I was a freshman in college, I was in science courses, gravitating towards biology and also towards bioengineering. But after a while, I started to figure out that what I really loved was, learning about science and telling stories about science, hearing stories about science. I didn't really like the doing of the science all that much. I wasn't a very good experimenter, and I really didn't like math as much as I think you have to in order to really do science. So I gravitated then towards, coursework that would allow me to follow those other passions. So courses about history, courses about writing. And I actually found a professor there. We actually didn't have like a history of science faculty, but there were a few historians of science where I went to college, which was Arizona State, who were doing history of biology. They were sort of sequestered away in the biology department. And so I found a professor there who I took a course from her, and it just sort of opened my eyes to the fact that there were people who really studied science and were asking the kinds of questions about science that I was interested in. Like, how do we know that? Why do we care about that? What got someone interested enough to do that experiment and try to find an answer to that question? So I kind of wound up pursuing history of science through that avenue. And because I was lucky enough to meet a professor who inspired me to study history of science by showing me the ways that could, open up these questions that I was interested in. And so I did that as an undergrad, and then ended up going off and doing a program in creative writing before coming back and starting grad work on history of science, and ended up doing a PhD in history of science without ever really thinking that I was going to work in a museum. But then here's another area where, I told you I was lucky to find an instructor who inspired me and taught me about history of science. I was lucky that, I'd gone back to Arizona State at that point and was pursuing a master's and didn't really know what topic I was interested in history of science, and found out that people at ASU were exploring Mars. And I started hanging out with the group of geologists who were working on instruments for an orbiting mission, and they were also working on an infrared instrument for Mars rover. And I thought, this would actually be something really interesting to write a master's thesis about. How did geologists start doing work on Mars? And so I did that, and years later, when a job opened up at the Air and Space Museum and they were looking for a curator of planetary science, suddenly it all kind of fell into place, and I kind of accidentally ended up as a museum person, and haven't regretted it ever since, because I studied history of science wanting to tell stories about science, and the National Air and Space Museum is a a great place to do that through exhibits and also through research and writing.
So I think that people who maybe don't work specifically in space sciences don't realize the importance of history in science. And I mean, specifically at NASA, I don't think that the layperson, when they're looking at some of the things that you have at Aerospace, will realize how important for NASA lessons learned and previous materials used, all of these things feed into our current program, and it's what makes us able to do something like the James Webb Space Telescope, for instance, which the technology is so important to the success of that mission. And that technology is all stored at the Air and Space Museum where you work. So I'm really glad to hear that you're writing about it and bringing these stories to life, because it encourages people to think about how much institutional knowledge we have in this country and how vital that is to our space programs and our military programs and all the other places where we use these things. So it's good you're there. I know you wrote a book that's out now on Harold Urey, who was a famous chemist from New York. And I found that book really interesting in that you reframed his life, or a lot of his stories, based on some things that are very relevant currently, and specifically his struggles with his upbringing and his strong religious beliefs and his moral beliefs around the development of nuclear physics. And so I really appreciated this book because it was something that I think was very relevant to a lot of people today. And I know historians have to go revisit people that other people have written on. So making it relevant now was really helpful for me. And the only thing I found that was similar in my understanding of history was sort of Charles Darwin's same struggle with his strong religious beliefs and the things that he was discovering in the physical world. And so I'll be interested, having just said that, I'll be interested to see what you do with your next books. So can you tell me about those, please?
Yeah, I discovered Harold Urey partly because of my interest in the history of planetary science and planetary geology, because Harold Urey shows up, during the missions to the moon, both the robotic missions that come before Apollo and then also during Apollo. And, he was really interested in the chemistry of the solar system and trying to figure out, as a chemist, how would you tell that history of the solar system? And so I discovered Urey in that context, and then found out that he had this incredible story of, having come from a very poor, rural, agricultural background and a religion that was also, very sort of almost similar to what we think of when we think about the Amish, being sort of so rooted to sort of basic, simple ways of life and farming and community, and that he had gone from that via, again, a very circuitous route to becoming a Nobel Prize winning physical chemist, and then getting involved in planetary science towards the end of his career. And so he offered me this great opportunity to look at where he had come from and how the questions he was interested in had developed throughout his life. And so in my new project, which is a history of Mars, I've tried to do that on sort of a bigger time scale, with Mars as the central focus, but looking at different periods of time and different places geographically on Earth where people were interested in Mars, and asking why were they interested in questions that they had at that moment, whether that was, in the Middle Ages, questions about medicine and astrology and even magic, and how Mars might relate to that in terms of its place in the sort of world machine that people believed that they were living in, where the planets and the sun and moon really participated in making things happen on Earth and causing change on Earth. Or in, more contemporary time periods like today, of course, where people are interested in Mars because it tells a story of, a path or a planet that took a slightly different path from Earth, but also gives us ideas about, if we could reshape that planet, whether that's small parts of it or the planet as a whole, could a human future exist on Mars? And if so, what connection would that future have to the problems of the present? Problems that have to do with anthropogenic climate change and other things. So really questions about how humans participate in the change of their home world, but also in the change potentially of Mars, of our sort of next door planetary neighbor. So, in each of those chapters, which follows a different time period, I try to look at where those questions come from, who the communities are that are interested in the planet at the moment, and what it is they're trying to do with Mars. So, for example, your community working today to understand the planets chemically and to explore the planets and prepare the way, for example, for human missions to Mars. Obviously, you have a very specific set of questions you're trying to answer with, for example, the upcoming Viper mission to look for water in the sort of shadowy craters of the, I think it's the North Pole of the Moon, or is it the South Pole? I can't quite remember. The South Pole of the Moon. So, I think that it's really interesting the way that these questions and these ideas of what we're going to be doing next, in this case, human exploration of the moon, sort of helps to dictate what questions you're going to ask and the methods you're going to use. And another thing I'm fascinated by in the sort of contemporary moment, which you're participating in again, and I'd love to hear your perspective on, is the way new modes of work have developed that involve having sort of what a colleague of mine who does sociology of this type of work would call sort of robotic ways of working, because you have these robotic co-workers that are on other worlds that you're working alongside and asking questions with, and sort of working in teams on the ground with that rover. So it's no one person is running the show. So there's obviously a lot of management that goes on, a lot of bureaucracy, of course, because it is NASA after all, and NASA is a government agency. But, I think it's perspectives like yours that I really want to learn more about, and that I'd like to ask you about now, on, what it's like to be an explorer in this sort of contemporary moment of using robots and large teams to explore the moon and also Mars.
Well, I'll tell you, the thing I love most about working at NASA is the opportunity to engage with these people, because they are really extraordinary. And what I find is that when people are so knowledgeable and so excited about what they do, then you do get a team that shares. And so you keep growing. I can ask questions and I can pass on information to young people, and it's really all about the teams. I've known people who are some of my best program managers and scientists, colleagues, who choose their projects based on the team, putting together the most, and they don't mean really just, the person most likely to win a Nobel Prize. They mean the people they like to work with, because it's such a good experience. And then there's another aspect to it that I think that you could contribute to a lot, which is I do a lot of work with planetary protection, which looks at trying to preserve the opportunity to do science on places like Mars. So if we take too many of our biological things before we have the science worked out, then that depletes our ability to know what went on at Mars. And also sample return is another thing. If we bring things back that are not healthy, that could cause a lot of issues. And through that, I've been to some conferences where people talk about some of the really deep issues that we're going to have to face. What happens if someone gets sick? Can they come back? What happens if someone perishes on Mars? Do we have an obligation to bring them back? And I think that's where history really will inform us at some point. I mean, it's very much like when the Europeans launched out to other continents, and a lot of bad things happened and a lot of good things happened. And it really depends on where you come from. But I think those are important questions that we're going to have to ask at some point. Where do we create those rules and those guidelines to help people like myself get it right? So I don't know. I don't know if you look at that at all in your books, but I think it's fascinating.
Yeah, well, I mean, there are definitely, you might say, historical analogs. The way that, people use Earth analogs to study sites on Mars, there are also historical analogs, I think, that could help us understand some of those issues. For example, the way that you mentioned the Europeans sort of going out and encountering the rest of the world as they did at the end of the 15th century. And, there were a lot of issues that came with those encounters and that contact. And as you said, some things that were very good, especially for the Europeans in terms of, building up the wealth of Europe and establishing European hegemony over a lot of the world. But a lot of things that were bad in the New World, which, were not limited just to, of course, the terrible treatment that some Native groups received, but also, the transplant, sometimes unintentional, sometimes intentional, of animals and plants, which I'm not, necessarily saying that those plants shouldn't have made their way here, but they had an impact when they got here. They sort of transformed the ecosystems of the Americas in interesting ways. So that might be a little bit of an analogy for what could happen if we do start bringing things to Mars, and maybe reasons why we should continue to be cautious the way that we have in sterilizing every lander and rover that goes to Mars right now. Because as you said, right now, the main priority has been not contaminating Mars in such a way that it would interfere with our ability to do science there. But if we start sending enough things and actual human infrastructure and humans that go with them, then those changes, or our ability to control what we're actually bringing to Mars, might not be quite as great as what we've been able to do so far. So, as that changes, we are definitely going to have to ask questions about, what is our responsibility to Mars? Obviously, when you're planning for the types of missions that you engage in, you must think a little bit down the line of like, what's the next step after this? Artemis is going to be going to the moon after Viper. We're going to be sending humans to build a permanent base on the moon and an orbiting space station around the moon. So, what does that look like, 20 years from now, 50 years from now? What do you think in terms of, someone who's actually dealing with these technologies? What's it going to look like?
Well, I think it's interesting in that it turns out the moon is pretty uniform. It doesn't have the same sorts of mountains and drastically different types of soil. But it also has some other issues, and one of the big ones is radiation. It's a huge problem, and thermal issues. It gets hot and it gets cold, like nothing we have here, except in very extreme environments. So I think that for the foreseeable future, anyway, the only path is robotics, and I think that may be also true on Mars, in that it's a long ways to go. And so, getting there and getting back takes a huge amount of energy. In fact, the current Perseverance is collecting samples, as you probably know, to bring back. And they have to send a separate spacecraft to bring them back, because they couldn't just lift off all of the stuff that they'd taken. So they have to send a little guy to pick up these samples from Mars and bring them back. So I think in the foreseeable future, we're really talking about a lot of robotics. And I think the Artemis program is rather cleverly conceived, in that the orbiting spacecraft for humans will allow a lot more immediate control. It takes very little time, and we don't have the same issues of bandwidth, of radio transmission, etc., that but we all know from our Skype or our Teams meetings, we don't have if they're closer, they won't have the same magnitude of problems with communications. So it's a well-conceived mission, but I think for a while now, we're going to be using robotics, which brings me to, I think you curate some robotic mission history at the museum. Can you tell me about that?
Yeah. I'm always happy to talk about that. It's true. I curate the museum's collection of robotic explorers, essentially. Everything from the very early Mariner missions of the 1960s up until our most recent rover missions to Mars. So, this is one of the coolest parts of my job is actually getting to help care for the robots that we have in the collection, and also think about what robots we should be bringing into the collection that help us to tell a more complete story of how we've learned to explore the moon and the planet. And when I came in, for example, we had 2 Mariners in our collection. We had Mariner 2, which of course was significant for having been the first successful interplanetary spacecraft that the US sent to Venus, and it gave us our sort of first flyby data from that planet. And then we also had Mariner 10, which was the last of the Mariners, and was the first spacecraft to use a gravity assist and to visit 2 planets on its mission, and to visit Mercury. So 2 very important spacecraft, but I didn't feel like that told the full story of the Mariner program. For example, we had none of the Mars Mariners, which I think were incredibly important. They gave us our first glimpse of the surface of Mars, and showed us that there were no canals, and there were no even simple life forms, at least that you could detect from orbit. And so I thought we really needed a representative of those Mars Mariner missions. And so ultimately was able to bring in one of the test versions of Mariner 9, which was the first spacecraft to go into orbit around Mars and to collect a sort of global photographic data set from Mars. And so I was very happy to be able to bring that in. But like almost everything that's in my collection, of course, the thing that I was able to collect is not the thing that went to Mars. Like I said, it was a test version. In this case, it was, I believe, built to test the propulsion system of the spacecraft so that they could figure out that it would be able to, do the necessary braking when it got to Mars and go into a good orbit for the mission. So, that's the case for almost every robotic spacecraft that I have in my collection, or in the museum's collection, I should say. Is that it is in some way a version of that thing that was used to figure out that it would work and to solve problems and answer questions, whether it was about a propulsion system or about whether or not different instruments would be able to speak to the computer once they were wired into it, whether the spacecraft could withstand all of the sort of shakes, rattles, and rolls that it was going to be subject to, right? So everything that I have that I brought into the collection and that was there before I got there is basically something like that.
Well, I think that's really important what you brought up about the collection, and it cycles back to what I was saying at the start of our discussion. I suspect people who don't work in space fail to realize that those things that are made as engineering units, we sometimes call them, are the things that you are collecting. Those are actually built to the same exact specifications, to the point where sometimes if something breaks while we're building, we'll go take the parts off of the engineering unit because it's been treated the same way. It's considered flight hardware. It goes through the same testing, the same rigor. So what you have is the same, especially those things that were what we call environmentally tested. They got thermal cycled and shaken, and they had their electronics turned on for interference testing and things like that. So really, in some ways, you have what was launched, whereas what's up there now isn't the same at all because it's been through radiation and thermal cycling and probably hit by some little micrometeorites and beat up. So you have the best of the best. That's exciting. Now, I'm at Ames. I work for Aerospace Corp, but I am stationed at Ames. And so I would be remiss if I didn't ask you about your book that's coming up on Kepler, because Kepler is a really, really important program for the Ames Research Center, NASA Ames Research Center. And I would like to hear all about what you're doing.
Yeah, well, that's a really exciting project for me because it's a different type of book than I've ever done before. We're actually, I'm working with a co-author who works at, a company that specializes in graphic novels, and he and I are writing essentially a graphic novel about the Kepler mission. And we decided early on that this wasn't going to be a book just about the telescope and its success in space, but it was going to be a book about how this telescope came to be, because it was a very long process of proposal after proposal until finally the Kepler space telescope was selected and started working towards launch. So in preparing for this book, I did a few interviews with one of your colleagues at Ames, now retired, Bill Barucki, who was sort of the lead in terms of putting forward these proposals one after another until finally Kepler was selected. And Bill, if you know him, he is a guy who is all about solving problems. And that extended everywhere from solving problems to do with how Kepler would actually work, to then also solving problems about, okay, the review committee decided that this aspect of the technology doesn't satisfy them. How are we going to now satisfy them that this technology actually will do what we say it will do? So, Bill was all about solving all of those problems, the technical and, you might say, like the bureaucratic problems as well, to get this telescope to fly. And, this all started actually when I visited Ames on a collecting expedition. I was there seeing what we could collect related to the Kepler mission. And what I found there, and what Bill and some of his colleagues showed me, was the Kepler technology demonstrator, which was a test bed that they had built to prove that the CCD optics they wanted to use would actually be able to detect the very small differences, the very small changes in light that happen when a planet transits between another star and the Earth. So it's a very, very small change in light, as I'm sure you know, that happens when the planet transits. And there were some at NASA in the various review committees reviewing his proposals who said, no, you can never make this work, not in space, not where you have a radiation environment that's going to be providing interference, and you have other things that are going to be decreasing the resolution of your optics. And so they built this test bed to prove that they could actually do it. And it's really an ingenious contraption. Forget designing a spacecraft. This was an entirely different process of figuring out, well, how do you simulate a planetary transit so that a CCD that you've put into, this test bed can then work to detect the transit. And so they tried to figure out little ways of creating a simulated star field. You had to have a light source. The light source had to be diffused so that it was uniform. You then had to have a plate with holes of different size, very small holes. And they decided they would simulate the transits by having wires that would go across each of the holes. And when they would run a current through the wire would expand, and that would simulate the change in light. But then they found that they had problems, which was that when you actually did that, they had circular holes, and the change in light was actually affected by the fact that the hole was circular and that the wire was expanding across the entire diameter of the hole. So what do? Bill, with his problem solving, said, you create square holes. You don't use round holes, you use square holes. So they redid the whole thing with square holes, and they ran test after test, running the thing for weeks at a time, simulating transits, running the data that was collected from the CCD through various computer programs and software that they had built for the mission, and proving that it could work. And so that technology demonstrator, which, as I said, doesn't resemble the spacecraft at all, um, is really, as you said, we often collect things that are, great representations of the spacecraft that flew because they were engineered in exactly the same way and built to the same specifications. In this case, it's something that was built to completely different specifications to solve one problem, which was proving to NASA's satisfaction that the technology they wanted to be used, or that they wanted to use, because remember, this is a discovery mission, so the budget has to be low. You have to buy a lot of your technology essentially off the shelf, which you don't usually do when you're building something to go into space. And so they had to prove that an off-the-shelf CCD could actually detect that small amount of light. And with the technology demonstrator, they did it. And when you look at this thing, it's great. I think it's great because it's got all of these loose wires and duct tape and other things that sort of, you would never send that to space, but when you're tinkering around in your laboratory, of course you're going to use duct tape and things like that you have handy to make things sort of position the wires out of the way of anything that they, have to be clear of. So I'm really looking forward to when we open the new Exploring the Planets gallery, which is going to happen later this year, because the public is going to get their first look at this thing, which is so obviously like a laboratory experiment and not a thing that was sent to space. And I think showing them that is going to be a lot of fun. But yeah, all of that is the long story of how we got started on this Kepler graphic novel, which
well, I think that's a really important story, though. I think that's a really important story because, the taxpayer gets tremendous benefit from these missions, and I don't think that they always understand, because you see these pictures of the magic of space, all the wonderful things, but it's those test beds where somebody goes out and figures out a CCD and how to make it better and how to make it radiation hard, that then lead to us having CCDs in space, which means then you can have your your nice map when you're driving down the street and you have an aerial view. All those sorts of technologies then that they put together with duct tape in the lab and test through all these hardships really help the American consumer and also the U.S. industry to have better products in the long run. So I'm very excited that you're collecting some of that too. I think that's really important and will really help the visitors to the museum understand the process that builds not just spacecraft, but everything else from their car GPS to their microwave oven, all the rest of it. So,
yeah.
Anyway,
well, oh, sorry.
No, go ahead. I'm excited.
Oh, I was just going to say, when people do come to the museum and see the spacecraft, oftentimes I think, because they've seen some of these things in books or on television or on the internet, they've seen the various Mars rovers and the images that they've sent back from Mars, but they very rarely have seen inside the laboratories, right? They don't know the numbers of people that are actually working to make that exploration happen on Mars, or for Kepler, in the case of Kepler, looking for exoplanets. They know the technology. They've seen the technology. They've seen the images produced by the technology, but they don't see the kind of messy work that goes on behind the scenes. And so that's what I love about the Kepler technology demonstrator artifact. But that's really like what I try to get at with a lot of the artifacts that we collect. So if I could give just one more example, we recently collected the testbed version of the Mars exploration rover, the Spirit and Opportunity rovers. And that testbed is beautiful itself because it looks like the rovers, but it doesn't have solar panels because it was almost always used indoors in an in situ laboratory where it was tethered to a power source and a control panel, and it was operated right there in real time a lot of the time, rather than the way that the rovers are by sending packets of commands up daily to do the work, that's been agreed upon ahead of time. And I love that the rover that we're displaying to the public looks like that rover, but at the same time, it has evidence that it was used on Earth. It doesn't have the solar panels, but it also has this very nice fine layer of dust on it that I've been trying to get people not to clean off of it when we were doing conservation, or any time that things get cleaned around the museum, because that dust comes from inside of that in situ laboratory, where they have simulant Mars soil that they've made out of various different components to make the environment as Mars-like as possible. So I want that simulant dust, that fake Mars dust, to stay on that rover for as long as I can, persuade people not to dust it. I really want to preserve that dusty state.
Wow. And I spend all my time trying to get rid of that dusty state. Trying to make sure it's clean when it goes and stays clean.
Yeah, right. Well, with Viper, again, I'm really fascinated by that mission, so I keep bringing it up. But I'd be interested to hear from you. You brought up lessons learned before, but what lessons learned with roving missions are being applied to Viper?
Oh, there's huge numbers. A lot of the modeling for regolith and where the dirt ends up. So we have wheels that turn. And one of the fun things is to go look at past lunar missions. And there was a lunar rover that was driven by humans, and they drove fast. And the regolith from the moon soil came up and sprayed, and they call it the rooster tail. Well, we're going very, very slowly because we're just trying to move from place to place and then drill holes to look for what's under the surface. Is there water? Are there other elements that we might, find interesting? So we did a lot of modeling to make sure that we wouldn't be kicking up dust that would end up on our solar panels and things. And that's been a problem for Mars. And we found that actually we're okay there. A lot of information on how the communications is going to go. That's really difficult. Power systems and how much the battery can charge up when we're on the dark side, because we're going to go into the dark side, or the unilluminated parts of the moon for periods of time and then come back out. So there's all kinds of things. And this mission, like Kepler, is a lower cost mission. So we're using a lot of off-the-shelf parts, a lot of things that we know from history. Some of our instruments, one of our instruments, M Solo, is an off-the-shelf spectrometer that Kennedy Space Center has rebuilt. We're using a lot of the technology that was used for LADEE to build spectrometers, with the same science team that we had on LADEE, which was a previous Ames lunar mission, a lunar orbiter. So yeah, there's huge amounts of technology that we're utilizing. The blanket people who have the thermal on this program is really hard. And so the blanket people are doing a lot to make sure that the blankets are not only going to keep the rover from getting too cold and freezing, literally, the battery will stop, but at the same time, it's got to be able to, the blankets on the bottom have to survive bouncing along over rocky surfaces. So they have to design special rugged blankets where I'm sure they've gotten help from other missions there. And then this mission is unusual in that we're using commercial launch services. So that's a new program that NASA's running called CLIPS, and they are contracting out launches and the bid process allows many groups to bid to take things to the moon. And so that's yet another thing that's very exciting, to try and drive down costs a little bit and improve launch technologies. So all kinds of good stuff. And again, very, very low budget for a rover. So hopefully that, and I think there's at least 2 landers coming before us that are going to the same general location and going to carry some of the same instrument designs. They're not exactly the same instrument, obviously, but they're designed to the same specs and to do the same job. And all of this is in preparation for the hope that we can utilize the moon, as you said, using this orbiter, which will be somewhat akin to the International Space Station, where people can go and run the robotics and receive samples and things that are built on the moon, possibly, and then package that up, just like they do things, taking things back and forth to the International Space Station. They could go back and forth to the moon and bring things and leave things. So it's kind of exciting. It's a good project. All right. Well, what's on your next collections list? What do we get to find in the next round?
Well, we just held not that long ago our annual Michael Collins Trophy event, where we give an award to we give two awards, one for lifetime achievement and one for recent achievement. And our recent achievement award went to the Ingenuity helicopter or rotorcraft team from the Perseverance mission. And I would love to collect one of the engineering models or test models that they built for Ingenuity. I would love to have that in the museum. And our director likes to joke that what he wants is for NASA to bring back Ingenuity so that we can then display it with the right flyer as two examples of the sort of firsts in aviation. And I love that idea. It's great. But in the meantime, I would love to have one of those engineering models on display and possibly just put it in the rover case that we have in exploring the planets, because we have there, as I said, the test bed version of Spirit and Opportunity, and we also have the flight spare of Sojourner, who was named Marie Curie. So we have Marie Curie, the test bed MER rover, and then we have a full-scale model that wasn't used for testing or engineering, but just for display of the Curiosity rover. And so I think it would be great to have Ingenuity in that case as well.
I agree. I bet you I bet you'll get that. I think you will.
Well, I hope so.
All right. Well, and are there other things that you think we can learn from the things you collect? Are there places that you would send people, or things you'd ask people to think about when they go to the museum?
Well, I mentioned the rover case, and I think that the rover case has a nice story that it tells, which is that one of the ways that we create new technologies and new technological capabilities for planetary exploration is by sort of working in increments, right? If you look at Sojourner, it's a pretty small rover. It didn't do a ton of science on Mars, but at the same time, it established a lot of firsts. It was the first rover that was able to drive directly up to a rock on Mars to collect mineralogical information from that rock using a spectrometer, and to relay that back to the lander and then to Earth. And that was a small rover, had a sort of short mission, didn't do a ton of science, but it paved the way for then that set of Spirit and Opportunity Mars exploration rovers to bring more tools and a number of spectrometers, an instrumented arm that could abrate material off of rocks and look beneath the surface patina of those rocks, and basically brought more robotic capabilities to Mars. And then you look at Curiosity and now Perseverance, these sort of small car-sized rovers that we've sent to Mars and succeeded twice now in landing them successfully, and then having successful missions with them. Those are heavily instrumented. They're essentially right? Roving laboratories with like full chemistry labs on board, practically. So, you know, working in increments through those three different rover types, you can see how you go from being able to do a little to being able to do a ton with technologies on Mars. And I think if that's any indication of what's going to happen next on Mars, obviously the Mars helicopters aren't going to be able to get too much bigger because of the limitations of the atmosphere. But I think you're going to see helicopters on Mars that, you know, can do a lot more than the current Ingenuity helicopter, which can take pictures and, you know, is an incredibly stable autonomous flyer. You know, evidently because it's still flying well beyond its initial test flights. Um, but you know, you might start seeing spectrometers and other instruments on board those helicopters in the future. And you might even see us exploring terrains on Mars that we haven't been able to explore, like, you know, the canyon systems and things like that, that rovers just haven't been able to get down into yet.
Well, that's one of the things that if we want to talk about iterative, the Viper rover has a drill on it. And one of the things that I know that's very often talked about on the Mars surface is that because of all of the atmosphere, which is very corrosive, there may not be evidence of things on the surface, but they might want to drill. And so I think that the drill, which is made by a company called Honeybee for the Viper mission to the moon, might one day also be something that would make it to Mars. And then we could repeat some of those Viking experiments in a place with soil that is, as you say, maybe a little bit of a better choice.
Yeah.
But we'll see. That's the whole Artemis program, is to try things out at our near neighbor, the moon, and then see where it goes from there. So yeah, it's exciting. I think there's some other exciting search for life. I love the idea of another Enceladus flyby. That's very exciting. You know, Enceladus has the spraying atmosphere, and so they can fly through that and get more information. I think that's a really neat idea. So there's a lot of good stuff out there. People looking for black holes and dark matter. Let's not forget the astrophysicists.
Well, you know, you mentioned the Webb Space Telescope, which I think is a really exciting mission. Obviously, there's going to be a lot of great, you know, astrophysics and non-planetary stuff that comes out of it. But one of the things I'm most excited about with that is that, you know, there's actually teams of scientists on that telescope that are going to be looking at exoplanets and trying to study exoplanet atmospheres with that telescope, which I think is amazing, that we could actually go from, you know, just not that long ago discovering our first exoplanets to now studying their atmospheres, which to me, I mean, the technology involved in that just seems incredible, because when you think of how small the exoplanet is, you know, at that distance, and how small then that thin layer of atmosphere is, like getting that data from so far away, just it floors me. And I can't wait to see what kind of discoveries people working with JWST make.
There's I'm going to give a plug to the MIRI people, which is the British contribution to that. And today I saw some pictures. It's the mid-IR range. And the difference between what they were seeing with Hubble and some of the other telescopes, ground-based telescopes and plane-based telescopes, and what they're seeing with James Webb is just orders of magnitude. So I encourage people to go look up some of the pictures coming off of that telescope already. It's just brilliant. I really appreciate the insight you brought to this, because I think that it's an important story that people understand, not just the importance of collecting and saving this for historical reasons, but also for technical reasons. and to explain to the public how valuable the technology is to their future and the future of their children. I think that really the Smithsonian is it's like our parks. It's one of those things that we just do better than anyone else in the world. And I'm so excited that you're there and helping to tell the story of NASA and the space race and our continued development. So I really appreciate your time on this. I really do. It's been such a pleasure.
Well, thank you. I mean, it's been a real pleasure to get to talk to you. And, I hope that you and all of your colleagues at NASA continue exploring our solar system and our universe, because, we want to keep building new exhibitions and collecting new stuff and talking about, this as sort of an ongoing human enterprise, as opposed to, something that we used to do in the past. And from all indications, it seems like the next decades are going to be filled with a lot of really exciting space exploration and science. So I look forward to watching that.
Thank you, Matt and Meg. I love the idea of future generations of planetary explorers learning from these special objects. Our executive producers, Colleen Stover, and our technical director is James Liggins. You can browse other episodes at csps.aerospace.org, or check us out on Twitter using #TheSpacePolicyShow. Thank you for joining us.